This video is designed to give you some ideas as to how to find the surface area of three different prisms. First of all, we're looking at a rectangular prism on slide 1. Finding the surface area simply means to find the area of each face of an object, a three-dimensional object, and add all those areas together. So if we were looking at a rectangular prism, that means it's a box, and there are going to be 6 faces, as there would be on a cube or a die that you might roll. So the idea is to look for an efficient way to find these areas and then add them all together. And of course, on this one, you're going to be able to recognize that you have 2 faces that are 3 by 6. So they each have an area of 18 units squared. You have 2 faces of 4 by 6. And they're going to each have an area of 24 units squared. And you're going to have 2 faces, the bottom and the top, of 3 by 4. And they're each going to have an area of 12 units squared, which means the surface area total is 2 times 18 plus 2 times 24 plus 2 times 12. You could also do 2 times the sum of 18, 24, and 12. And this is going to get you 36 plus 48 plus 24, which is going to be 108 units squared. Now, the idea, of course, is simply to find an efficient way to do this. And since each of the faces on this box is a rectangle, it's easy to do 3 times 6 to get 18, 4 times 6 to get 24, and 4 times 3 to get 12. You simply need to visualize what each face looks like, create it for yourself, and then find the area of that two-dimensional face. Add them all together, and you get the surface area. On this second slide, we have a triangular prism, meaning that we have 2 triangles as their face. So here's one of them, and there's one on the back behind us. Okay, and we also then have 3 rectangles around the perimeter of those 2 triangles. So there's a rectangle that's a roof, there's a rectangle on the back, and there's a rectangle at the bottom. Now the idea is to identify the size and shapes of each of those faces. So of course, if we look at the back, we have a rectangle that's 5 by 12, which has an area of 60 centimeters squared. Make sure you keep the units in mind. We have a bottom or base that's 8 by 12, and it's useful to draw these each time. That gives you 96 centimeters squared. And we have a roof that is something by 12. We'll call that X for now. And X is that length of that diagonal of the triangle. So we're going to need to use Pythagorean theorem to find X. So off to the side, it's useful to draw our triangle, which in this case is a right triangle, indicated by the little square in the corner of the triangle on the drawing. So that means we can use the Pythagorean theorem to find X. So 5 squared plus 8 squared equals X squared. 5 squared is 25, 8 squared is 64, and that's going to be equal to X squared. 25 and 64 is 89, and so X is going to be the square root of 89, which is a number between 9 and 10, obviously. So let's calculate that. Square root of 89 is approximately 9.43. So now we know that this is a rectangle on the roof that's 9.43 times 12. If we multiply that by 12, we get approximately 113.2 units squared, centimeters squared, excuse me. And now we simply need to add the two triangles in. So each triangle then, the area of a triangle is 1/2 the base times the height, and that's going to be 1/2 then 8 times 5. 1/2 of 40 is 20 centimeters squared, and we have two of those. So that means our area total is 60 plus 96 plus 113.2 plus 2 times 20, or 40. And all of that added together then is going to be, let me use the calculator just so I don't mess this up, approximately 309.2 centimeters squared. Remember that the roof is of course not the same size as the base or the back for that matter, because the roof is slanted and it has the hypotenuse of this right triangle rather than the same length as the base. So it is not 8 by 12. That's a common mistake. It is whatever x is, which we've discovered was 9.43, since that's the hypotenuse of this right triangle. So there's a place to keep an eye on. Make sure that you recognize that these are three different sized rectangles that go around the perimeters of these triangles. Finally, for our third slide, we have a cylinder. And once again, you need to identify how many faces there are, or how many surfaces there are that you need to find the area of, and then identify what those surfaces are and find their areas. Now, the difference here is that we have a little bit of a tricky one. Obviously, you have two circles on the top and the bottom. Each of those has a radius of 7. So that gives us an easy thing to find the areas of. But then we have this label that wraps around the can. Now, you're tempted to say that it's some weird circular shape. But in fact, of course, if you unroll a label around a can, that label is going to be a rectangle. The rectangle is going to have exactly the height of the can. So the height of this rectangle is going to be 9 centimeters. And the rectangle must be long enough to wrap around the circle. In other words, it's got to be long enough to go all the way around here when you roll it up. So that means that this distance here is actually the circumference of the circle, or 2 pi r. Now that means we have a rectangle plus two circles. So the surface area total is 2 times pi r squared. That gets us the areas of the two circles, plus the area of a rectangle, which is length times width. So it's 9 times 2 pi r. We simply need to use our radius to find what those numbers are. That's 2 times pi times 7 squared plus 9 times 2 times pi times 7. And of course, this gives us 49 times 2, which is 98 pi. And 9 times 2 times 7 is 126 pi. So we could actually combine those two together and collect our pi's and get 224 pi centimeters squared, and that would be a legitimate answer. Oftentimes you're asked to multiply that out, and therefore you should multiply 224 times pi, which gives you approximately 703.7 centimeters squared for the area. So keep in mind that the tricky part here is recognizing that you have a rectangle whose height is the same as the height of the cylinder, assuming that you've stood it on its circular base, and whose length must be enough to reach around the circle, meaning it must wrap around the circumference of the circle because it must follow the perimeter of the circle. So that piece right there is something that is often found to be fairly tricky, but if you just think about the logic of it, it makes perfect sense. Useful to draw each shape and represent the dimensions of it as carefully as you can, and recognize what the shape is and use appropriate formula for it.